Hello everyone, my name is Fang Chonghua, who works in Science and Technology on Electromagnetic Compatibility Laboratory and China Ship Development and Design Center in Wuhan, China. It's my pleasure to make a presentation online for all of you. I'd like to share my recent work with you. Today, my topic of presentation is the computation of quantum radar cross-section for the regular five-pointed star. And it's me, and I am a senior engineer in our institute. And that's my email, which means you can contact with me. Here is my outline. The first part is introduction of my work, and after that I will show you some theory information about the quantum radar cross-section calculation. And then I'd like to talk about the simulation results and the discussion. Finally, we will get to the conclusions and some ideas. Let's get to the part 1, introduction. As you know, quantum radar offers the prospect of detecting, identifying, and resolving Earth-based platforms and weather systems. In the electromagnetic battlefield, quantum radar may become a revolutionary technology, just as the RF space technology was during the last several decades. When we talk about the quantum radar, we should not ignore this guy, Marco Lanzagrota, who works in NRL, Naval Research Laboratory in USA. Because the concept of the quantum radar was first proposed by Dr. Lanzagrota in his book in 2011, Quantum Radar. In that book, he has systematically built up a theory about it, and barely shown that it aimed to cope with the stealth weapons threats, such as from J-20 in my country. You may ask me a question: what's the quantum radar? What's the definition of it? In general, we can define a quantum radar as a set of detection system that use microwave photons and exploits some form of quantum phenomena to enhance its capabilities to detect, identify, and resolve targets of interest. As quantum radar emits a handful of photons at one time and receives some photons. Here, a handful means several, maybe 1, 2, and 3 photons in one pulse at a time. The radar target interaction in this region is described through photon-atom scattering processes governed by the laws of quantum electrodynamics, QED. We should note that the law is not the classic Maxwell equations, so that the quantum correlations serve to improve the resolution and SNR. Let's see the many potential applications of quantum radar technology, such as detection, identification, and discrimination of stealth platforms, and the space exploration, and planetary defense. And in this slide, I'd like to draw your attention on the third one, biomedicine, because the quantum radar can be regarded as a kind of non-invasive measurement method for the detection of cancer due to its lower power, very low power. Why? Because in one pulse there's only a hand of photons. Do you remember in last slide? In this slide, I will introduce the definition of quantum radar cross-section, QRCS. You may hear about RCS, but maybe you have no idea about QRCS. Actually, there's a need to develop a concept of quantum radar cross-section to objectively measure the quantum radar visibility. Analogous to the classical radar cross-section, CRCS, the equation of definition, QRCS, has been introduced by the Marco Lanza-Grota. Based on the wave function of the photon from QED, he has shown that QRCS of the rectangular plate and revealed the quantum effect of side-lobe enhance. In this slide we can see the scenario of incidence from a single photon, and that's the equation for the definition of QRCS. However, definition equation is very not useful. It usually not very easy to use, so that usually we will use that equation instead. And in the right picture, you can see the QRCS and the CRCS curves in this picture. In this green circle, you can see the part of QRCS are larger than that of CRCS, which means side lobes enhance. That's a kind of quantum effect, according to the Dr. Lanza-Grota. Let's see, another guy is a very important person in the progress of algorithm for QRCS. Dr. Matthew. In the Pennsylvania State University, he has improved the algorithm for the regular 2D targets such as triangular and circular planes. And with his work, we can use a more convenient equation, this one, than that from Lanza-Grota. However, due to the complexity of the orthogonal projected area, a vertical atom of the three-dimensional targets, that a little work has been done about the QRCS design of 3D targets and some other 2D targets. Therefore, the computation of QRCS of the typical targets of interest, such as the regular 5-pointed star, are worth demonstrating. Therefore, in this work, we presented the interest curves of QRCS and the CRCS for the typical regular 5-pointed star, which is never punished before. Now, let's see the part 2 theory. Actually, this theory is about the algorithm that can deal with the QRCS calculation. We usually call it as a kind of 3-step method. The first step is projection. Here, we should have all vectors on the surface of the object. Make the projection on the plate, the k vertical is the normal and get the coordinates of the projected point. After that, we should do the step, the second step, rotation. With the twice coordinate system rotation transformations, we can transform our coordinates to the plane of a vertical item so that we can get 2D coordinates of the projection points, which means z components are 0. Finally, the third step is triangulation. Using that triangulation class in MATLAB software, we can create a 2D triangulation from a set of projection points with 2D coordinates. And finally, we can get the area of it. Let's get to the part 3, simulation results and discussion. Based on the questions introduced before, we use the normal algorithm to calculate the QRCS case with a single photon incidence by ourselves. We should note that the single photon incidence scenario is the normal one. From the picture in the left of slide, we can see the geometry of the 5-point star with the detailed geometry information, which means the coordinates of the 5 points. And from the picture in the right of this slide, we can see the mesh model of that 5-point star. Now you can see this picture, the mesh is very good, so that we can be confident with our simulation and results. From that figure 2, according to the green arrow, we can also see the distinct quantum effect of the third-level enhance, which means QRCS are larger than that of CRCS. Here, the curves of CRCS are from the typical physical optics method (PO) from Altair Facal software. So, how do we understand that result? According to the analytic expression of the peak value in QRCS curve for the 2D planes in previous work, we can use that equation, this one, which means the calculation for the maximum of QRCS. Here, the A item, the A symbol, denotes the area of the regular 5-pointed star. The peaks in the curve at theta equals theta with 0 degree should be about 24 dBsm, which QRCS values exactly are. Notes have verified the accuracy of method to some extent also. Then, for the rectangular 5-point star, as we can observe, the side-lobe quantum effect can be seen, especially in the angle dome, such as 60 degree to 19 degree nearby on trade. Finally, we should show our conclusion. Okay. In this paper, a new calculated curve of QRS for the regular 5-pointed star was demonstrated. We also observed the similar side lobe quantum effect in the comparison between QRS and CRS. And therefore, more dedicated in study on the case of experimental for verification are left for the recent future study. In the last slide, I will share you with some my personal ideas. First one, we are preparing to carry out the first expression of QRS for both 2D and 3D targets in the world, because so far there's no such experiment in this world. Idea 2. To complete other researches such as diffraction and multiple reflections in the calculation of QRS algorithm. Oh, thank all of you, and it's my pleasure to end my presentation, and that's my other two connection information for you, so that if you have any question, I'm very happy to answer your question from email and other form. Thank you for your attention, and that's the end of my presentation. Thank you. Bye.